Good morning. My name is Marshall Michel. I have the pleasure today to be with our fine panelists to talk about HPC using OpenStack, and I'm going to let them introduce themselves. I love technology. It's really 9 a.m., right? Please, if you have questions, please take a look at the Etherpad. We're going to do it the usual OpenStack way. We're going to have you please ask your question in there. Obviously, we have a microphone. We welcome microphone question, but it helps us try to control flow of information so that we can try to guide it to the right person. So with that, Stig?
Hi. Oh, hello. My name is Stig Telfer. I work for a specialist consultancy called Stack HPC in the UK. I've been involved in OpenStack and HPC since around about the Havana cycle when I was working at Cray and doing R&D projects for HPC infrastructure management using OpenStack then. We've been running Stack HPC for about 3 years, and that is really the essence of our business. So I'm the CTO there.
Grab that. Morning, everyone. I'm Blair Bethwaite. So I'm Solutions Manager at NESI, which is the New Zealand eScience Infrastructure. Previously, I was a HPC consultant at Monash University, and there I was building HPC on OpenStack, and have been doing that for a while. So I'm now running interference in that domain at NESI.
I'm Tim Randalls at Los Alamos National Lab. I work in the HPC design group, and one of the hats I wear is integrating cloud with our HPC resources and finding out how we can use cloud technologies to augment the HPC systems that we're running at Los Alamos.
Hi, I'm Mike Lowe. I work on the Jetstream project at Indiana University. It's the National Science Foundation's first production cloud system for doing science. And we have 2 clouds, about 320 nodes each.
I'm Mike Moore. I am Director of Software Engineering for Business Integra, but I'm entirely working as a cloud engineer on our contract at NASA Goddard. And I've been there for 2.5 years, and we're running about 80 node OpenStack cluster that we're going to be upgrading soon to 160 nodes.
My name is Ryan Dooley. I work at Data Machines. I'm Director of Platform Services and Solutions. I'm also PI of the Agave project, which is a science as a service platform for the open science community. Been around for, I don't know, in this year, probably not quite as long as most of these guys, but I have a little bit more experience on the user and platform side.
Cool. Thank you, guys. We have our introductory question, which usually will help you try to understand a little more what their users do and what the architectures that they're running is. So I'm going to go with Ryan, you start, and we come back that way.
So we have a diverse group of users. Primarily, we're pushing a lot of machine learning codes through containers and Kubernetes and OpenStack, and helping onboard users to get their research done and hopefully move primarily DARPA-based projects forward.
In our cloud at NASA, we have also a varied user group. The HPC type users are mostly doing engineering, rendering, CAD rendering. There are some users who are running Python code to simulate various astrophysical things. The users themselves, some of them are system engineers, some of them are scientists, and there's a various level of support. Some completely take care of themselves. Others, we have to do 95% of the setup for their jobs.
So the solicitation that funded us asked us to solve a problem for the National Science Foundation. They've got about 350,000 people who can use the national infrastructure, and about 2% do. So we set about to solve that problem. We have about a little over 2,800 users and a little over 400 different projects. So the use cases are extremely varied. We have lots and lots of education. If you guys saw the pictures of the black hole recently, The pipeline for that was prototyped on our system and then moved off to Google Cloud. So we do all kinds of things, and if you have questions about that, I can talk about those later.
So at Randall, we've been running HPC systems for a long, long time, but we're very, very conservative about how we manage them. Uptime for us is paramount, I think. So not that it's not anywhere else, but we're very, very conservative in upgrading our management infrastructure and how we run our clusters. We're still using Perseus to deploy our systems. I don't know how many of you have ever heard of Perseus, let alone know that it was forked and became Werewolf at some point. But it's unmaintained. We maintain it internally. So I'm trying to bring us into at least the late 20th century by adopting some better ways of managing our systems and taking more of a cloud DevOps approach to being able to do that is one of the efforts that we have underway. Another use case that we have is trying to alleviate some of the problems we have with a limited number of login nodes and not unlimited number of users, but a lot of users who are pretty sure they're the smartest guy at the lab. And if they feel anything is wrong on a login node, they start typing top and PS and start putting in trouble tickets saying, Mike's compiler's been running too long on this front end node. So things like that. So we're trying to prototype a system of virtual private login nodes so everybody just gets their own VM-based cloud, an OpenStack provided VM to serve as a login node to the cluster. And then they won't know if they have a noisy neighbor. And I think that's, it feels a little disingenuous, like we're trying to pull something over, on them, but at the same time, they'll spend more time doing science and less time worrying about someone else. So
It's a good theory.
hey, we'll see if it works.
Okay, so I might talk about this from the perspective that I had in my last role at Monash. So, our cloud HPC use case was essentially just to provide a HPC platform, but on top of a multi-tenant infrastructure as a service environment, so that we could then spin up new instances of the HPC service, because there's, of course, a whole pile of stuff that's not easy to do in a multi-tenant sense in a HPC environment, even today. Storage is a major issue, which I'm sure we'll probably talk about. And so that's really how we came to running HPC on top of OpenStack. At NESI, we have cloud capability alongside our large supercomputer and cluster, which we just use for virtual lab type environments, but they're really not cloudy at all, other than there's a couple of guys in the back end who will be using OpenStack to create that infrastructure. The users never see any of that, and they don't have root, they can't self-provision. And that's because there's several petabytes of GPFS that we don't want them anywhere near touching without appropriate permissions.
So we have a broad range of clients, and if I was to say that there are any sort of common strands between them, I guess that there are inherently three tensions which pull against each other with modern research computing, and that is to get deployment of non-traditional or unconventional application stacks. So a lot of emerging software packages and emerging science domains are using things which don't fit into a conventional batch computing model, and research computing institutions who are faced with the challenges of getting those application environments into their data center and meeting the needs of the users who are not being represented otherwise by conventional batch. They turn to cloud computing for flexibility. At the same time, they kind of want to get the users off their back who are wanting to deploy these things, so they look at the self-service and the sort of the ability to self-administer these platforms as well. But the third point of tension is how to do that in a way which is retaining performance or some semblance of it. And so a lot of the people we work with come to us with those kinds of needs.
So we're gonna go through quickly the next set of questions. We're gonna ask only one or two panelists at a time to answer the next set. And those questions are usually helpful for us to try to help you understand what our perspective is, but we'll soon reach the common questions. So, related to performance, we are always told, hey, I need a cloud, but is a cloud a better solution for you running your HPC? So I'm thinking either Tim, Mike, Blair.
What's the actual question?
Performance. Can cloud compete with HPC?
Yes.
Go for it. Go for it.
I would say yes. And the long answer is yes. I think it's kind of a nuanced question because cloud is not just one thing, it's a spectrum of different configurations. And you have this kind of balance all the time between the performance that you're extracting, the overhead, versus the convenience for administration and for users as well. And really, you're able to choose your own adventure on that spectrum and trade off between the level of performance you get versus the convenience. But even at the most inconvenient but most performant case, and where you're going on a sort of a bare metal path, it's still way more convenient than conventional HPC to manage and operate. And that means that, and you sacrifice no performance for that. So it's pretty compelling, I think.
I like that.
And you can then manage it in the same way as your cloud.
Yep.
Okay. All right. So let's move along onto the productivity. You know, which tools make it more useful for your researchers? I'm specifically asking about researchers in that particular case to build on top of. Go for it.
Well, this ties into the last question about performance, and that's we have Charlie Cloud was developed at Randall to be as close to bare metal as possible, but something that is a container by just using user amount namespaces. And I know at a conference like this, cloud and containers are pretty much, pretty tightly intertwined. Conceptually, people think about them a lot of the same ways. Around my users who care most about performance on large multi-physics, tightly coupled MPI applications, I can't say the word cloud because they immediately go to this performance thing and they're like, no. But I can talk about containers and they're okay with that. So from a productivity perspective, they really want container technology, just don't sell it to them as something that looks like cloud. They don't want to hear that. And they think that they're going to pay some sort of penalty for that.
Thank you. So moving forward, users have rights, privilege, access control. Well, how do you give them access to the resources they need in order to do what they want, with the given software? What's your service model, right?
Well, at NASA, we give everyone access to Horizon self-service, and they can install any of the packages they need from CentOS or Ubuntu or even Windows. Mm-hmm. And if they break the rules, we point the finger at them.
Okay.
Yeah, for our users, I have a colleague who likes to say he spent 30 years keeping people from giving root, and now he hands it out like candy at Halloween. So, that's one of the biggest shifts is that, yeah, you get this thing, you get root, go do whatever you need to do, and we will get out of the way. But we're also there to help you if you need us.
Okay. All right. So I think you can keep the microphone because I want to talk about
okay.
science gateways.
Yeah, that's a big deal for us. So that 2,800 active users I referenced doesn't count these science gateways. One of the big ones that we partner with is Galaxy. I believe they have about 100,000 users total, give or take. Yeah. And if their jobs fit a particular profile, they have a whole bunch of machines that back it. Some at UT Austin, I think some are at Pittsburgh, and they also use some virtual clusters on Jetstream. If they fit this profile, they'll run on this virtual cluster running in our cloud. And I think 8,000 people, no, higher, 12. Do I hear 12? 12,000 users. Yes, okay. my colleague over there handles a lot more of the user-facing stuff, so he keeps tab on that. But 12,000 users have had their jobs run on our system. They never knew. We really didn't know until they come back and until the Galaxy project comes back and reports that, hey, you know, this year this is what ran on your system.
So, thank you. The next question is actually going to be for Michael Moore, because it's about data compliance. So like you let your user do what they want, and then you slap them on the wrist. So can you explain a little more about how you make it possible for you to trust your user to work with the data that you give them?
Sure. Well, most of the time it's their own data or it's considered public data, what they're starting with. But we also have in-VM scanners that report what software is installed. If they install something without a license, we can audit that. We have network scanning in each tenant that's coming so that we can see if they have an insecure configuration even within their own tenant network.
That is pretty nice. So that one, I guess, is a question I added some time ago about Cloud Federation. But I mean, you know, Jetstream has its own model, so we're gonna move that one. Cattle, not pets. I think that was that you, Blair? No. So we are slowly evolving the workflow model toward, you know, a run once type architecture. People, you know, we talk about containers. We design to the problem. We keep the information around, and then we're able to redeploy it as we want. So are we slowly evolving toward a model where HPC is turning into a service model better than a large computation to solve a problem?
Yeah, definitely you see that. So there are nice emerging use cases where things like Slurm compute partitions, sort of these HPC resources, can be provisioned on demand in service of single jobs or in service of a growth or spike in workload. And that whole sort of use case of building a hybrid cloud environment in which the elasticity is really high and fits with a batch model at the same time is something that we are seeing coming out more and more now. People are starting to not just provision what they had in their data center, but in a cloud context with the layer underneath, but actually to start thinking more flexibly about what that can bring them.
Yeah, and that's also ties in to the conversation we're having, that you give their own projects basically to people in order to give them the sense that they have access to a private cloud in that mode, which I guess ties into.
I might.
Yeah, please.
Make a follow-up point on what Stig was saying, maybe. I feel like in the last decade, we've actually maybe gone a little bit backwards with regard to HPC as a service for people to consume remotely, i.e. from grid computing days. I mean, if people that are actually fundamentally running compute-centric kernels and doing, you know, whatever it is, whether it's parameter sweeps or optimizations, high throughput type workloads, they can be running on any number of resources. They might be cloud-based. It might be a regular HPC cluster with a Slurm or whatever. But we now don't have any sort of de facto standard for submitting jobs to these things remotely. There's no standard REST API anymore for job submissions. So I mean, there's a few projects around. Things like Open on Demand is one example that looks pretty interesting to me, but haven't touched it yet. So I'd be interested in anybody who actually does run it. Yeah, so I think that's an area that we could do with some new work in. Maybe.
Thank you.
I'll put in a shameless plug and say that Agave does give you that API and interfaces to do all that. Yeah. I also would like to point out that, you know, for a long time we had this growth in HPC, and we were building these larger and larger clusters. And when you actually logged in and looked at the user bases didn't really change that much, right? I mean, Mike touched on a point that, you know, they're supposed to serve, 80 to 100% of the scientific community, but they were only really supporting 2%. That 2% takes a long time, right, to go through their career and retire. So you had the same people running the, essentially the same codes over and over and over. And what we're seeing now with the kind of the democratization of resources through cloud and through container and through just much more accessibility to compute, on demand or out of necessity, you're seeing a lot of people that are attacking their problems in different ways, right? Not everyone needs MPI. I mean, that's just the reality. A lot of people need distributed computing, but very few of them actually really have demands for systems like that. So yeah, you're seeing maybe a step backwards in the number of people that are crying and saying, I need HPC, I need it. But you know what? They didn't need it in the first place, right? What they needed was accessibility, they needed moderate performance, they needed just time to get their problem solved. So I think it's fair to say that the people that really, really needed to do HPC that were already doing it are still doing it, right? What you're now seeing is the other 98% having a seat at the table.
I'll keep the microphone. Sorry, Tim, you wanted?
I was just going to follow up to say, I think Ryan's right in that our lab is a poster child example of a place that's been running essentially something that looks like the same code base now for 30, 40 years. And what we're starting to see more of a generational split in our users, so our core mission's around these applications. But as we get more and more people in who've sort of come up through school and through university with these other programming models, that says Jupyter Hub on there's one, notebooks, which, whatever. I don't want to go there, I don't think. But, and other task-based frameworks that are being developed to try to help this problem of the MPI application where I lose one node or one, my whole application dies. My 4,000 node application might run for 10 minutes, it might run for 10 days, but as soon as there's a hiccup, the whole thing falls over. And Legion and these other task-based frameworks that are being developed, it's a paradigm shift that gives us more resiliency. So we're seeing our bread and butter MPI folks are starting to see the resiliency that comes from the cloud community and what they're doing, and they're looking at their applications that traditionally have to run an HPC system, and they're saying this probably isn't the best way to do everything anymore. So it is a big shift, but I think it is highly generational, and it's going to take time before, you've also got 30 years of knowledge built into these applications that we have to somehow move to a new model, and it will not be easy. It's going to be a decadal process probably for us. But it's something I think we realize we have to do if we're going to ever get to exascale with any resiliency at all. Because I'm waiting to see what runs on an exascale class machine at MPI at any scale and how long that thing actually runs before it all just falls apart.
Blast runs at exascale.
Oh yeah, embarrassing.
Let's move on to the multi-tenancy question. So Ryan, why don't you explain the topic here?
Yeah. So how many people work in a data center, like admitting or supporting it in some capacity? How many people have more than one resource there? Right? Are those like HPC clusters, or do you have multiple clouds? Multiple clusters? Multiple clouds. Okay, yeah, so you guys have a pretty well-defined solution for onboarding people to use different clusters, right? You get a login, maybe we have some queues, we partition stuff, we have some sort of quota, and yay, we're good, right? And that's wonderful, right? But when you start deploying these cloud resources, with all of the good work being done here by Airship and by the Kubernetes community and Ironic, it's trivial to stand up, plug in a rack and stand up another cluster. And so many people are doing that it's just, hey, it's a great idea. We have a new project, let's stand up a new rack. But pretty soon that starts to sprawl, right? So now you have, you're moving slowly from the days of, I have a computer in the closet to, oh, I have a cloud in the closet, right? I have another cloud under my desk, and I have another cloud over here, and we have 15 clouds in our data center. And those things become unmanageable and unwieldy so fast, right? So now you want to consolidate again, but you don't have the concepts of multi-tenancy at the level and depth and richness that you need them to pull off the same kind of stuff that you're pulling off with single system batch schedulers, right? So more of a question to throw out to these guys about how you're addressing that, right? That fundamental need of growth and heterogeneity within your cloud environment to support these kind of things.
I think multi-tenancy is the key disruptive element that cloud brings to HPC environments, because up until now we've kind of been creating the same stuff, and now we can do things with multi-tenancy and the control over sharing and the control over isolation, which enables us to do stuff which cannot be done outside of a cloud environment, really, realistically. And that's the key transformation, really, is it's enabling this whole kind of controlled access, sensitive data workloads, and enabling people to share where they can and to isolate where they need to as well. That's fundamental, I think. So.
Thank you, Rand. We're going to move on to the first few questions that were asked. So, is Arwen in here? I know who has that one. What type of accelerator are you using behind GPUs? Some of us might be using FPGA or ASICs or other type of specialized hardware for acceleration. So how do you integrate it, and does it give you access to, what are the pain points?
I think the key accelerator that we've been using is not a processor, but the network device. Mm-hmm. And we've been doing a fair bit of work with how to make networking truly performant in a cloud context. And so I think we haven't used FPGAs in that sort of environment, but we certainly make heavy use of InfiniBand and remote DMA-enabled Ethernet, and also the OVS offload work that Mellanox have been doing recently has got great potential to be a big transformer for performant networking.
What are the pain points?
Oh, setting it up. It's coming a long way, actually. I mean, I think since we first looked at it, the evolution has been very rapid, and I wouldn't bet against Mellanox on anything.
Yeah, I mean, in my work at Monash, we did a lot of GPU integration with OpenStack, and that's just moving into vGPU now. But also the network. I mean, we were very early to adopt Rocky, RDMA over Ethernet there, and that's now evolved to be quite mature. At the time, going back a few years, it was very hard to deal with from a debugging perspective, getting any visibility. I mean, Ethernet's not that great compared to InfiniBand for that anyway, because it's unmanaged, so you don't have a subnet manager that you can go and ask about what's going on the fabric. But the other problem is that then you've got hosts, and you've got this extra level if you're using KVM, then you've got another extra level between the host and the guest that is difficult to introspect on, and that there weren't that many counters available to actually go and look at, and certainly no standard tooling to do so. But I guess that's all changed quite a bit in recent years.
So here you bring up some topics of multi-tenancy, handing out root access like Candy and RDMA. How do you keep tenants separated from each other?
Yeah. Okay. So I'll repeat the question. So basically, how do you keep tenants separated from each other if they've got root access, but you're trying to do RDMA, maybe using InfiniBand? So I mean, in my experience, we were using Rocky, and so you can do VLANs, and if you're doing virtualized HPC, then you've got the ability to tie a specific VLAN to a particular SRIOV virtual function. So as long as the hardware does what it's supposed to do for isolation, then there's no way for the tenant to see anything else that's on a different VLAN on the same physical network.
Yeah, and there's a similar arrangement for InfiniBand as well. In a virtualized context, it maps to a segmentation ID for a tenant network to a partition key. And there's also an equivalent capability in the bare metal world as well. I can see 2 people here who are doing this already. So,
yeah, for our virtual private login node project, if you run an image that we provide, you don't have root in it, and your file systems get mounted. If you bring your own image, you can't mount any file systems. You're put into a different provider network, and you can't get to any access. Project network. And so you can get to your data, but you're essentially syncing against a file transfer node to get that data in and out of your VM. We just don't let people do that. For things like RDMA, all of our nodes are job exclusive, so we don't ever put more than one user's application on a node at a time. And that's just how we've always done it. As we get to larger, higher and higher core counts, our codes may not be scaling that way. We're finding a lot of people on a 36-core machine are running 4 MPI ranks because it's the most efficient way for them to run their application. They don't really care what they're doing to the resource as long as they're getting their science done quicker. So we're starting to think about how can we use probably containers, because I don't think we want to go the step of full-blown cloud for HPC jobs yet, but containers, C groups, what does the resource manager let us do to isolate tenants on the same machine, to see if we can even approach this in a way that doesn't make certain security-focused people pull all their hair out. The GPU one in particular is not, so to the accelerator question, we have GPUs, we don't have anything else. We found that the container technology is letting us use the GPUs much more rapidly to get different science done than we used to, because now we can pull in a container for something like TensorFlow with GPU support and be able to use it. A lot of our application development teams haven't spent the past decade working with CUDA or OpenCL. So this is a way that we're leveraging the GPUs by being able to access something done by someone who's an expert in that technology while we sort of grow that inside of our own organization.
Yeah, it's pretty nasty to do inside of containers, right? I mean, that's not a pleasant thing to do, to try to lock those down and keep users happy. I'd be interested in hearing how many folks are really taking more of a SIOPS approach to this. I mean, we talked about a lot of different science gateways, and those are interfaces to science and to the systems and to how you're doing stuff. But another valid approach that more and more people are taking is more of a DevOps approach to getting their runs and their experiments done, because it provides reproducibility, provides a much more collaborative environment, and takes away them having to really understand how to interact with the systems, right? And so we've provided that abstraction. We help them build their containers, apply best practices, and then we isolate everything because they're not the ones actually coming in and running stuff, right? We can run it on their behalf with total isolation and security.
Yeah, you said DevOps, and we have a revolution inside of our lab right now around continuous integration and continuous deployment. And being able to use the CI process pipeline to do things like build container images using Docker files when we don't want users to ever have privileges, we can put them in an isolated virtual machine-based environment where the CI process is launching the Docker build for them, and then we have this automated workflow that lets them use industry best practice tools to develop these containers, even though we don't actually use the Docker runtime on our systems.
So I was also going to ask you, are you looking into Docker in Docker, for example, to try to add a layer of separation, or adding you can also force Docker to run as a specific user, if you are forced to use Docker, like NVIDIA Docker, for example, thing like that.
We still have the problem of, so no, we're not doing that.
Okay.
What we want to do is we want someone like Docker to take the Charlie Cloud or Shifter runtimes and just implement that and then support it for us, and we'll maybe buy it back from them. But as things stand today, I think it's too big of an ecosystem to try for us to get our heads around and how we would actually deploy that in production. So we went the other way, which was let's build the smallest, most concise container runtime possible that we're comfortable with, and we won't get any of the frills that you get from Docker. I mean, I think Docker Compose is a wonderful thing. I'm not going to re-implement that. I want them just to give me run HPC that uses nothing but user and mount namespaces or something similar to that, where I don't need all this other abstraction that is a penalty you might pay with cloud. And I don't want network namespaces for my application. I just don't need raw device access to my GPU and to my InfiniBand device.
Tim, just a question on that. Something that has been a pain point for us, because we use containerized science workloads quite extensively, has been this sort of huge disconnect between the containerized runtime environment and POSIX file systems. So how do we actually, is there any way we can actually maintain user IDs and group IDs so enabling a containerized workload to actually access the user's data on a file system? Because the way we see it at the moment, you can map all the processes within the container to a particular user, but for some dumb reason, you can't actually set a group for them either.
You can set a group for them. You can set one group with an unprivileged namespace. You need privileges to be able to map more than one group. So that's a problem where we have a big shared scratch file system with a bunch of project directories and they want to share stuff between them. And it's nothing that we've really tackled yet, but the users are just saying, just get us container technology and then let us manage our own data, as long as we have access to that file system. So right now, what we do is we simply bind mount in our Lustre scratch file systems, which is not an ideal way of doing it, but we haven't run into that mapping problem as long as they...
I think it's through Kubernetes where we hit this. So.
Oh, okay.
Yeah, so having done some of that, I have a question, a follow-up question. When you tell Docker or your runtime to give you a specific ID and group ID, you're cutting yourself off from the group IDs that you've set up in your own Docker file. Meaning, I have a user and I want to sudo, I can't anymore because is that something that you're looking into, or?
I'm not sure I totally understand the question.
Well, so you say you give them access as a group, right? As a specific group. Do you make it possible still for them to? How do you make it possible for them to retain the privilege that they have within their own container? It's okay. It's a multiple group.
Cross any privilege boundaries. Yeah. They stay who they are everywhere.
Yeah,
it's not necessarily the user in the container is the same UID as what they are outside the container, because they can call themselves root, but the kernel's user namespace mechanisms map that back to their outside UID.
When you start Docker, you can specify a different ID and user UID and GID, but it's okay. I mean, I'll follow up with you after on that.
So there's some nuances there in the way Charlie Cloud works versus the way that Docker works versus like Singularity that addresses this in a completely different way. If you're familiar with BGFS, they have a pretty good.
Yeah, you're familiar.
They've done a lot of work in this area trying to get those user IDs and group IDs mapped in there and kind of overlay the POSIX namespace into your container and back onto the host. That's one way to do it. I think everyone that I've seen doing it at scale has done it the way Tim mentioned, where you just, hey, the people who are running the user IDs inside the containers are the same as on the host. That is a great argument for implementing a DevOps process, right? For auto-building everyone's container yourself, right? 'Cause I know at Data Machines, we built a cloud service to do security scanning of every image that's going to run on our system, right? So we catch that stuff. We can catch user namespace violations. We can catch privilege escalations, security exploits in libraries are using. All those things just go towards not us wanting to be, in that position as a security authority, but us just needing to provide a better experience for the end user, right? So I think that's a great step to take.
And you're also reinforcing the conversation about CI/CD to try to make things, more efficient for the users and for the operators. So, those on the
Question over here, Mike.
Sorry, yeah, please. Okay, microphone if you can.
So coming back to the accelerators related question, I had a question. You guys seem to have already clusters and racks operating. How many of you people have something other than NVIDIA GPUs, and what is the comparative percentage apart from NVIDIA GPUs? And if you have something else from GPUs, could you give some percentage Or even if there is a demand from users apart from NVIDIA GPUs, like from AMD or Intel?
About a year and a half or 2 years ago, I tried to get my hands on some FirePro cards. I don't know if they actually exist. I asked Dell, they didn't have any. So.
So I assume it's all NVIDIA GPUs.
So my last job, we had a few thousand accelerators, right, from Intel. And the problem that they were running into was kind of a critical mass, right, that you have to rewrite your code to make efficient use of those, right? And you can use their SDKs, and they have some code conversion stuff, and that's wonderful. But if you're trying to squeeze performance out of there, which is kind of the reason that you do these things, you're rewriting your code, right? And there's only so many cycles that people have to go back and rewrite their code on the funding that they have and the time frame that they have. So if your commitment to those GPUs or their existence isn't going to last, longer than their funding cycle, then it's going to be really, really hard to convince them to, fool me once, right?
But have you guys considered the price parity between NVIDIA GPUs and AMD? I assume there's a huge gap between similar performing GPUs with the price.
I think there is also the fact that a lot of the optimization is done for CUDA, and you only have one way of getting CUDA, CUDA compatible processors. So
it's all NVIDIA through.
Which is why you can't get a discount on those parts.
Yeah. So we're actually running very short on time. Thank you. Just a quick follow-up. The question here, please feel free to come and ask us. Jacob, I know you're. We're going to have a session. A lot of the users here that you see are going to be at the PTG tomorrow. So if you're ever at the PTG and you want to stop by the Scientific Special Interest Group session, it's tomorrow at 9 a.m., I think. We're going to be continuing conversation on setting up a user story and other models for us to continue collaboration like we have. Apart from that, please thank our speaker, our panelists, and thank you very much for joining us today.